The heavenry of stars hung with humid night blue fruit, mused James Joyce in his unparalleled Ulysses. In another of his ravishing sentences, he ponders about the vastness of the age of stars when he says, "So-called fixed stars, in reality ever-moving wanderers from immeasurably remote eons to infinitely remote futures, in comparison with which the years, 70, of allotted human life formed a parenthesis of infinitesimal brevity." Joyce had an almost unmatched mastery with words. In another of his classic, Finnegan's Wake, which is a reversal of Ulysses, he wrote a sentence that was later to be immortalized in the world of physics. 3 quarks for master mark. Quarks, as is now known in the world of physics, is the elementary stuff, that is, something without any underlying substructure out of which protons and neutrons are made. Democritus, the great Greek philosopher, thought atoms to be uncuttable, the building blocks of matter, but it is these elementary particles that, in the truest sense, are uncuttable. It is the interactions of these quarks, along with the forces that bind them, that is gluons, that give rise to the mass of the matter in the entire universe, ranging from the heavenry of stars to the unfathomable depths of black hole and everything in between. But how does mass come about in the first place? All of the universe is permeated with something known as the Higgs field, much as the life of a fish in an ocean is surrounded with water. It is the interaction of the particles with this field that gives rise to mass. If you imagine that there is a shoal of fishes in a pond, all of whom we could think of to be the Higgs field. Now suppose 3 different kinds of fishes come across the shoal, one of which is the kind of the shoal itself. This fish might not interact with the shoal and pass without perturbing the Higgs field, and therefore have no mass. Another kind, a larger one, that is a smaller predator, might scare or disturb the fishes in the shoal and interact with the Higgs field and acquire some mass. A super predator, like a whale for example, scares and interacts greatly with the shoal, the Higgs field, and acquires greater mass. In the real world, photons that make up light do not interact with the Higgs field at all. Different types of quarks interact differently with the Higgs field and have different masses. When the universe came to life out of nothing, as some theorists propose, it was an incredibly dense object, and unbelievably hot too. Only after it cooled due to expansion did it have the right conditions to give rise to quarks. After a millionth of a second after its formation, quarks aggregated to give rise to protons, neutrons, and electrons. Only after 380,000 years did the universe cool enough for the electrons to be trapped around stable orbits outside the nucleus and formed the first ever atoms, hydrogen and helium. About 200 million years later, the first stars were formed. Right now, there are about 100 billion stars in every galaxy, and the number of these galaxies is thought to be 1 trillion. Given that a star like the Sun can hold about 1 million Earth-like planets, is it even sensible to ask whether the universe is light enough to float on water? Well, every question is a shout-out to know the universe. Given that the universe is not simply stranger than we imagine, but stranger than we can imagine, as Heisenberg brilliantly put it, it's well worth asking the question. Besides, we also know that our planet Saturn, despite having 100 times the mass of the Earth, can float on water due to gigantic volume that makes it incredibly light. But measuring the volume of the universe is a different ballgame altogether. This is because we don't quite know the boundary of the universe, and for all practical purposes, we shall never do. This is because of the boundary problem in the universe. Well, the universe is only 13.7 billion years old, and this means that the light in the universe has had only so much time to travel. And so has information, because there's nothing that travels at a speed greater than the speed of light. But our observable universe is about 93.5 billion light years across, and the large-scale structures of the universe reveal to us that the matter in the universe has spread out evenly, meaning that they must have interacted with each other at some time in the past. But given that light has had only 13.6 billion years to travel, how has information traveled at a distance much more to make the universe homogeneous? An answer to this conundrum was posed by Alan Guth, who put forward the theory of inflation. He theorized that soon after the Big Bang, the universe expanded by a factor of more than a billion of a billion of a billion in a matter of a fraction of a billionth of a billionth of a billionth of a second. In other words, the universe has expanded as much as that tiniest fraction of a second during inflation as much as it has ever done since. This gives the matter in the farthest reaches of the universe time to interact just before inflation kicked in. And how much has the universe expanded ever since? Well, we don't really know, and we shall never really know as well. This is because the most distant galaxies are being pulled apart from each other due to the rapid expansion of space. The galaxies that are nearer to each other, such as the Andromeda and the Milky Way, have a greater gravitational force of attraction than the energy of empty spaces between them. Other galaxies that are further away have a greater energy of the empty space than the gravitational pull, and as a result of the distance between them is ever increasing. In the future, as the expansion of the empty space continues, the galaxies will be so far apart that there will be no traces of other galaxies, as they will recede from each other at speeds greater than the speed of light. So, given that the universe is expanding so much, we can never truly know the density of the universe. We can only know the density of the observable universe, and this too is varying. During its origin, the universe was infinitely dense. Then with inflation, this changed. After inflation, 13.6 billion years since, its density is mere 9.9 times 10 to the power minus 27 kilogram per meter cubed. This is as low as taking all the mass of molecules in a cubic meter of air that we breathe and expanding the volume as much as the space between the Earth and the Moon. So yes, the observable universe would float on water, given you could go outside the universe and find as much water. But space and time and matter and water, all of these things exist only inside the universe. There is no outside. And since the edges of the universe are flying apart from us at speeds greater than that of light, we shall never know what is the boundary of the universe. Are there other universes too, in a great multiverse with a different density? We can only speculate. Such are the ever-changing tracks of never-changing space, as James Joyce so memorably put in Ulysses.